I will start. I'm glad to have a chance to present my work here. And I don't know even, do I need to present myself a bit, but this slide shows us the necessary information. My work is called an implicit linear difference equations over some finite commutative rings. I'm sorry. So to start with, let's go deep to history a bit and consider, let R be a commutative ring with identity and A be F sub n be given elements of this ring. Consider the linear difference equation 1 over the ring R. This equation is called to be implicit if B is a non-invertible element of the ring R, and it's said to be explicit otherwise. An explicit linear difference equation 1 always can be transformed to the form 2, and for each given x sub 0 from the ring R, its solution is defined in a unique way. It has a unique solution which is defined by the formula 3. When we have to deal with an explicit linear difference equation, the things go a bit harder. Another way. For example, consider the implicit difference equation 1 over the ring of integer numbers. This equation was studied recently by hierarchy of mathematicians Gefter, Goncharov, Pivarny, Gerasimov, and others, Martinyuk, and especially as over the ring of integers, it was studied, for example, in the work 2. Consider now the example. The equation 4 has a solution, the general solution 5 over the ring of rational numbers, but for any given constant c, we won't get solution in integers. The theorem 1 establishes the solvability criterion for the equation 1 over the ring of integer numbers. Equation 1 has a unique solution in integers for any sequence of integers F sub n, if and only if b is equal to 0 and a is equal to plus minus 1, which was proved in the work you may see as numbered 3. Now let's go to our problem. Denote that sub-m a residue class ring modulo m, and let p be a prime number. Firstly, describe the commutative rings with identity of order p squared. This classification was given in the work in the paper of Fine, but especially when we have to deal with commutative rings with identity, it happens that there are exactly 4 different commutative rings with identity of order p squared. These are the residuum class ring modulo p squared, the sum zp plus zp, direct sum, also the Gauss field of order p squared, and a special ring, which we call that way, that polynomials of over zp, where t squared is said to be 0. As an interesting fact, if we denote Rp P from S. The following quotient ring, where S is some number from ZP. The following properties of the ring Rp of S hold. Firstly, if either P is 2 or S is equal to 2, it's the special ring. In the case 2, if P is greater than 2 or S is a quadratic non-residue, it is a direct sum of two fields, ZP and ZP. And if otherwise, if P is greater than 2 and S is a quadratic residue, then it is isomorphic to the Gauss field of order P squared. Now we have an interest to come back to our one second. Come back to our linear difference equation 1 over the ring R. And we have an interest to solve it over an arbitrary ring commutative, which is commutative, has unit, and of order P squared. Pay attention to the fact that solving it over the field is not much interesting, because we can divide in the field in any case if it's not a zero element. And thus the most interesting cases are solving it over the special ring and over the direct sum of two fields. The equation 1 over the ring of over the residue class ring was discovered in it was studied in the paper 5 recently, and the solvability criterion for each was gained. So now we pay attention to two theorems, and first of which is the case of the direct sum of some fields, the finite sum of finite sum of finite fields. So let I be an index set from 1 to R, where R is natural number, and each k sub I is a finite field. Denote A and A, B, and F sub n those elements. Rest F this index denotes just the place of element in brackets, and also introduce the following denotations for E sub B, I sub A, and I sub F. I sub is all indexes for which B sub is equal to 0. I sub is denoted in the same way, in similar, and I sub F is all indexes for which f I n is equal to 0 for all n. Then the following assertions hold. Firstly, the equation, I'm sorry, it's not formula 1, it's equation 1, has finitely many solutions if and only if the sets IA and IB do not intersect. Moreover, the amount of solutions of the equation 1 is equal to such number n. In particular, the equation 1 has a unique solution if and only if B is zero element and I sub n is an empty set. Secondly, the equation 1 has infinitely many solutions if and only if intersection of A IA and IB is non-zero, non-empty, but is a subset of I sub f. And otherwise, the equation has no solutions. The equation 1 has no solutions if and only if such an intersection minus IF is a non-empty set. And the next theorem establishes the solvability criterion for the most interesting case, for the case of special ring, which is actually a ring R2 of 0. Let me remind, I think, what is RP of 0. It's just a special ring ZP of T factorized by T squared. So let B be not a zero element of this ring. Denote A, B, and F sub n in the following way. Just A0 is a coefficient without T, A1, B1, and F1n is coefficient which is before multiplication on T. And all this A, B, and F are the elements of the ring Z2. The following assertions hold. Firstly, the equation 1 has finitely many solutions if and only if either A0 is not equal to 0 or B0 is not equal to 0. Moreover, the amount of solutions of the equation 1 is equal to such a number n. In particular, the equation 1 has a unique solution if and only if B0 is equal to 1 and A0 is not equal to 1. Secondly, the equation 1 has infinitely many solutions if and only if A0 is equal to B0 and is equal to 1, is equal to 0, and F sub 0n is equal for 0 for all n. And the equation 1 has no solutions if and only if A0 is equal to B0 and is equal to 0, but F sub 0 n is not equal to 0 for some n. The number of slides is quite a mistake in this presentation. So on this moment, I say thank you for attention. It's all from my presentation, and I am ready for being questioned.
Thank you for presentation. What profound results. Please, if anyone has a question, proceed. Professor Yampolsky, please.
Thank you for your talk. Probably I have a funny question, maybe. Your ring is finite, right? But the theorem said that the equation for 1 has infinitely many solutions. How it can be? The ring is finite, but the number of solutions is infinite.
It's explaining it in as a simple example. We can consider the ring Z as a residue class ring Z sub m, and as you know, as equation of kind I don't know 2x is equal to 0. It the modulo 4 has a non-trivial solution. X is equal to 2, and if we compose that x, if we mix zeros and twos for different n, we get I'll just write an example of like we'll get all these sequences where twos and zeros are mixed in all way, and this is actually as minimum as 2 power z different sequences. Of course, it's infinite. Being more simple, it's we can just take all the solution, all x sub n as zeros, and take something like sequence even numerated. Is sequence is just delta e 1 n multiplied by 2, something like this. I mean, where all coefficient, all x sub n are zeros except a particular one, and of course it's different sequences.
Okay, thank you.
Any other questions?
It seems no. Thank you for your presentation. Thank you for questions and suggestions.